Hello everyone, welcome to the third video on linked list, and what we're going to be doing in this opportunity is to actually write the linked list class. Now this linked list is going to be a governor of my actual list. This is the one that is going to keep track of where my elements are, what order they have, and also to make sure that it creates these links between the nodes. Something pretty much what we did in the previous example, in the previous video, but in this time we're going to have a logic that allows these to happen automatically as I add elements to the list. So let's get to it. The first thing I'm going to do is I'm going to create a new class that I'm going to call my linked list. The reason I'm calling it my linked list is just to avoid any conflict that I might have with any other class in Java called linked list. So I'm just going to call it my linked list. And well, in this class, we need to keep track of a couple of elements. Well, we've said already that even though I won't have any array or an array list internally, what I'll have instead is a reference to the first element in the list. So my first element in the list is going to be a node. So that's why I'm going to call this as a private node called first. But then there is another element that we need to keep an eye on, particularly if we want to add elements in either way, in either end of the list. So if I want to add or remove elements at the front of the list, or add or remove elements at the back of the list, then I need to have also a reference to the back element or last. So if I do this, this is going to be very easy, very helpful, because I can have access to either end of the list. Now, the next thing is I should be able to keep track of how many elements I have in the list. So if the list has something like 10 elements, then I should be able to know or to have a variable to keep track of that value. Perfect. Now, the next thing I'm going to do is for this list, I'm going to add a constructor that allows me to initialize the list itself. And in that constructor, I'm going to initialize the three parameters, the three attributes that I have in the class. So this.first is equals to null. Why? Because if I'm creating a brand new list, that means that there is nothing in there. So my first is null, my last is also going to be null. The other thing that I can initialize straight away is the size. I know that the size at the beginning or as I just start the list doesn't have any elements, so the size is going to be 0. Now notice that for a linked list, I will not have an array as an underlying structure. I will not have a map. I will not have any other structure. I will only have reference to the nodes that are relevant in the list. So the first, the last, and the number of elements that I have. Now, let's start thinking of the behavior of this class. And this class will have a couple of different things, but one of the most important things that I should have is I should have a method that allows me to add element to the list. And we already know that this being a linked list, I should have a reference to the first element and the last element in the list. So if that is the case, if I have a reference to the first and the last, then I should be able to add or remove elements from either the front or the back. So let's start with let's break this down into smaller pieces, and let's start doing a method that allows me to add elements to the front. So in other words, what we're going to do is we're going to receive a new element that is going to be pointing to whoever is first, and this first pointer is not going to point to the element that it was pointing before. It's going to be pointing now to this new first element. In that way, the order of my list remains the same, just with another element at the top. So let's go and let's do that. So I'm going to create this public void add first. So we already know that the add first method should receive a node, which I'm going to call a new element. Now, if we follow the instructions that we just draw now, I need to do a couple of things. I need to change my reference. I need to say, for the new element, their next element is going to be whoever is first in my list. And my new first element is not going to be whoever was there before. It's actually going to be the new element. The other thing that happens in this situation is, because I'm adding a new element to this list, now my size is also going to increase. This is brilliant, but there is a couple of things that we need to keep an eye on. So what happens if I'm adding a first element into a list that is empty? Well, if my list is empty, that means that both my elements first and last are pointing to a null object, that there is nobody there. So as soon as I add a new element, well, yes, it is true that this first is going to be pointing to that, but also my last element is going to be pointing to that. Because if I only have one element, that element is both first and last. So that's something that we need to keep an eye on. So how do we address that? So we need to have a little bit of a precaution in here, saying if the size of the list is 0, meaning that the list is empty, not only I have to do whatever I did already, but I also need to define that the last is equals to my new element as well. But something to keep an eye on is that this only happens if my if the list is empty. If the list is not empty, because I'm only adding to the front, whoever the last is going to keep remaining being the last. So there is nothing really special in here. Okay. So the next thing I'm going to do is before we try to start testing this list, I want to create a method that allows me to print what the actual the content of the actual list. So how do I do this? Well, first of all, I'm going to create an override method that is going to contain, that is going to be the toString method. So it's going to be the method that is going to call anytime I want to put this to the console. Now, a couple of things that I can do in here. So let's think about the logic of this. So I need to print each one of the elements, or I need to find a way to print each one of the elements that I have in the list, starting from the first one to the last one. So what I can do is I can create a variable string that I'm going to call to return, that I'm going to initialize with a bracket. And then the next thing I can do is I can consecutively loop over all the elements that I have in my list. And this is one of the first algorithms that we're going to see how, that we're going to try to implement in this particular structure. So let's go and say, for example, not for a while. And I can say, we're going to create a variable called current, which is going to be of the type node. So who is going to be current? So current is going to be the node that I'm going to be trying to print at the particular time. And we're going to do that in a while loop, so I can go and loop over over each one of the elements that I have in there. So my first element is going to be the first element. So the current node, I'm always going to start with my first element in the list. So I can say, as long as current is not null, so I can say that to return is going to be plus equals to my current element dot toString, because we already have a toString method in the node, plus a little space. I'm just putting a little space so we can print that in a neat way. And then after I have printed that, I can say, well, my current is now going to be my current getNext. So what that is going to do is going to allow me to loop over each one of the elements without having to say that getNext. So let's have a look at this. My current element start with first. If first is not null, it will put its name inside the array or inside the string. And then I move current to the next element. And this is going to happen consecutive times until I find an element that is null. So the final thing that I need to say is that the toReturn variable is going to close with a square bracket, and now I can finally return the toReturn variable. Brilliant. So this is something that we can already start testing. So let's save this. Let's go back to my main method. And now let's create, I'm just going to get rid of what we did in the previous video. Just going to leave the nodes and the people. So now what we're going to do is we're going to create a new list. Is equals to a new my linked list. And now we can start adding elements in there. ll.add first. I can only add first because that's the only method we've written so far, but I can add first, for example, n1. I can add first n2. I can add first, for example, n4. So if we print this list, we should be able to see the elements in the order that I have given. So I added first n1, but then I added first n2, and then I added first n4. So my first should be n4, then n2, then n1. So let's see if that is true. There it is. My first element is n4, which is Pocahontas. My second element is n2, which is Alice, and my last element in the queue or in the list is Amilcar, because I've been adding people to the front. Now the next thing that just to expand the functionality of the linked list would be to create a method at last. So now, for the add last method, it's exactly the same principle as before. We just need to keep in mind some slightly different considerations. So the method would be something similar. So public void add last, but in this case, it's the same thing as before. I'm going to be adding a new element. So what happens when I'm adding a new element to the back? Well, first of all, I don't need to set a next element for the new element because the next element is going to be null. That's just the end of the list. However, I do need to go to my last element, and I need to say to him, hey, your next element So hey, your next element is the new element. The other thing that I need to do, this is not get but set, perfect. The other thing that I need to do is I need to update my reference to the last element. So my last is going to be equals to this new element. And of course, my size is going to increase. So in this case, what we've done is saying to the current last element that the new element is his next, and then changing the pointer to the actual new last. There is another couple of things that we need to keep in mind if the list was empty. Because if the list is empty, I need to also do a couple of things. I need to also keep an eye on a couple of things. Well, the first thing is that this is empty. This new element that I'm adding to the last is going to be the last, but it's also going to be the first. So that's something we need to keep in eye. So we need to say only if it's empty, first is also going to be equals to the new element. And that's only the case if the list is empty. So as you can see, the logic, the principle is exactly the same as adding first. I just need to keep an eye on what elements I'm adding to each other and how the references are happening in there. So the next thing that I would do is, once that we have this, would be to test this to make sure that we are on the right track. So I'm going to save everything here. And just the same way I have added if a couple of first elements, I'm going to add one element to the last. So for example, I'm going to say at last N4, and I'm going to say LL at last. And this is going to be N3. So what are we expecting? So I'm adding first N1, then I'm adding first N2. So I'm expecting to have N2 first, then N1 later. Then I'm adding last N4, so that would be the next element, Pocahontas. And then I'm adding last N3, which would be John. So that is the order that we are going to be expecting here. And as we expected, as we predicted, that's exactly what we're getting. So first of all, I'm getting my node 2, which is Alice. I'm getting then my node 1, which is Amilcar. Then I'm getting my node 4, which is Pocahontas. And finally, my node 3, which is John. Now, just to complete the functionality of this list, well, if I can add the elements first and I can add the element last, so I should be able to remove the element as well from both the back, the front and the back. So I'm going to create a method here. Let's start from the front, and let's say public void remove first. So this is going to be a method that is going to allow me to remove the first element in the list. Now we're going to build this step by step because this might be a little bit overwhelming, but let's break the problem down first. Well, the first thing that I know is that if I'm removing that element, I should return that element. So my method is not going to be void, it's going to return a node. So I'm missing a return statement in here. So what node are we going to return? Well, we're going to return the first element of the list, which is the one that I'm actually removing. So I'm going to put that in a variable, and I'm going to say node to return is going to be equals to whoever is my first element. And if I have it there already, I can go and say return to return. Good. Now that I have defined who am I going to return, then I need to start playing with my references. My new first is not going to be first anymore. It's going to be whoever goes after first. So that would be my first that get next. So my new first is going to be whoever was in a second position. Now, this might not work in all of the cases, and those are the special considerations that we need to take before we go with the special consideration. There is something else that has to happen. My size has to decrease. So now that I have managed to remove an element in a generic situation, well, the next thing that I need to do is I need to consider a special situation. So suppose, for example, my list is empty. So if my list is empty, I really don't have anyone to return, and definitely my first that get next is something that is going to break, because if it's empty, that means that first is null, and null trying to get the next from null is going to give me a null pointed abstraction. So that's something that I need to keep an eye on. So I'm going to say if the size is 0, I just want to return null. There is nothing else I can do because there is nobody to return. Now, but what happens, for example, if the size is 1? So if I have one element in there, there is a slightly bigger thing that I need to keep an eye on, which is the fact that my last pointer is not going to point to the first anymore, so that one has to change. So I need to say if size is equals to 1, and this is only happening if size is equals to 1, last is equals to null. Now, I don't have to keep an eye for first, because if I only have one element, first is already pointing to null. So my first is going to be pointing to null straight away. There is no problem with that. Now, to make sure that this is working, let's go and let's give it a go. Let's go to the main method and make sure that this is working. Perfect. So I have added two first, I have added two last. I'm going to print that list as it is, and then I'm going to remove a first, and I'm going to do it twice. So hopefully what it should be able to see is that my final list has only two elements because I've removed first twice. There you go. So let's run this. So there it is. When I do remove first, twice Alice and Amilcar get removed, and I have a Pocahontas and John there. Now, just to make sure this is actually working correctly, I'm going to call this 4 times, and we should be seeing that this is actually working correctly as well. So we'll deal with all of the possible scenarios. So when I have only one element, when I have two elements. So for my remove last method, I have a little bit of an extra challenge, and the problem that I have is that each one of my elements only have a reference to the next one. Now I do know who the first one is, and I know who the last one is. But let's think about what happens when I want to remove the elements. So all I need to do to remove the element is to remove this linking here. So I need to say to this element, which is the second last, that you're now pointing to null, because last elements always point to null. But I also need to say to last that you're not pointing here anymore, you're now pointing to the second last element. So that's something that we need to do. The problem is that we don't know who that guy is. The problem is that we only know this one and this one, but I don't have a reference to this object in here. So what we're going to do here is we're going to leave these last, remove last, for a later stage. Instead, we're going to try to find we're going to write a method that is going to allow me to find the element in a given position. So if I know who is the element that is in the second last position, I will be able to find him. And then once I find him, I should be able to actually remove the last. So let's do that first. Let's create a method public that is going to return a node, is going to give me a node, find element by position. And of course, the parameter of this method is going to be the position of the element that I'm looking for. By convention, we always, in computer science, we always start counting from 0, and that's exactly the same thing that I'm going to do in here. I'm going to consider that my first element is my position 0, my second element is my position 1, 2, and so on. So what do I need? So I need a couple of things. Same thing as before, the same thing that we did with the toString method. I'm going to create a node that I'm going to call current, that first of all is going to start in whoever my first element is. And then I'm going to start counting on a counter that is going to be an integer number that is also going to start at 0. That means that when my current pointer is pointing at the first, my counter is going to be pointing at 0. But if my current counter moves on, my counter has also to increase. Now, now we can start doing a while loop, and I want to start moving forward in the chain, advancing the element. How many times? Well, as many times as I need to reach the position that I'm looking for. So as long as counter is lower than the position. So I'm going to say current is equals to current that get next, and also counter plus plus. Perfect. Now, once I do this, what that is doing is incrementing the value of the counter and moving as many times as the counter needs. And the needs to get all the way up to the position. So finally, when I get 1 before the position, it will increase and then it won't loop anymore. That's when putting counter lower than the position. So it will increase. That means that my counter is finally going to get the position that I'm looking for, but also my current is going to get to the position that I'm looking for. And now that is the node that I'm going to return. Now I'm going to say node return current. Brilliant. Now, how do we know if this works? Well, let's give it a go. Let's save this. And let's go to the main method and let's try it. So the next thing that we can do is we can say system.out.println, and I can say ll dot find element by position, and I can say, for example, I want to find whoever is in position 0. There it is. In position 0 is Amilcar. If I say position 1, is Pocahontas, and if I say position 2, I'm getting here John. Now, there is a couple of things that we need. Again, there is a couple of things that we need to keep in mind. So, for example, what happens if I put here a value that is bigger than my size? So if I put a value that is bigger than what I have. So that's something that I need to keep an eye. Well, it's telling me null. It's telling me that it doesn't exist. And what happens if I go for something even bigger? Let's say, for example, I put 4. So my program is going to break because I'm trying to find an element that is outside the range of my list. Also, there is something else that we should keep an eye there as well, which is the fact that maybe the list is empty. So if the list is empty, I should do something about it. So that's exactly the next thing that we want to consider. We can add an if statement to look after those situations. So we can say, for example, if the size is equals to 0, return null. So I'm saying I just want to return null. But also, I should return null if my position is bigger than my actual size. So if my size is 3, my position shouldn't be bigger than 2. So I'm going to say the same thing if size is equals to 0, or my position is bigger or equal than the size minus 1. There you go. So if my position is bigger or equal than the size minus 1, then I'm going to return a null. So that's covering all my possible cases when things can go wrong. So let's give this a go. Let's go to the main method and let's run this again. So hopefully what we'll get instead is a null object as opposed to a nasty null pointer exception. Yes. And if I don't remove elements, but I put something like, for example, at this point I know I have 3 elements. If I say 3, for example, which would be out of the range, I'm getting a null as opposed to a null pointer exception. And something else that you could do is you can actually throw an exception in there. I'm not gonna do that because that would be beyond the scope of what I'm looking for. Perfect. Now that I can find an element by its position, well, that's brilliant because now I should be able to remove the last element. Why? Well, because I now know where that last element is, or the second last element is. So I invite you to stop the video maybe for a couple of minutes and try to give it a go yourself, and let me know how you get on. So the remove last method is going to also, just the same thing as the remove first, is going to return a node. It's going to return the last node. So this is going to be remove last. And again, I don't need to put a parameter in here because I know what element I want to remove is whoever is the last. So the first thing I know is that that is the last element is the one that I want to remove. So I'm going to save him in a reference. Node to return is going to be equals to whoever is last. And I know that is the element that is going to be returned at the end. Now, let's do a couple of things that we need to do. Well, as we said before, I need to be able to find whoever element is in the second last position. Now, I know my last position is my size -1. So my second last position is going to be my size -2. So I can find my second last using the method that we just wrote, which is find element by position. And the position that I'm looking in this case is size -2. So once I have found the second last position, then I can start playing with the references. So I can now say second last that set next element to null. And I can also say my last is now whoever the second last is. And finally, every time you're removing an element, you need to decrease your size. Now, this is a really, really good start, but it's not perfect. Let's see why it's not. So what I'm going to do is I'm going to save this, and I'm going to give it a go. I have my printing here that have 4 elements that we've been adding. So I'm going to say ll remove last, and let's see what happens. So when I run that, yeah, it seems to be working. John has been removed. Let's do 2 removals instead and see what happens. Yeah, seems to be working. Pocahontas have been removed. Let's see what happens when I do 2. When I do 3 removes. Yeah, Amilcar has been removed from the list. Let's do 1 more, and with that should remove everybody. Well, Alice hasn't been removed, and the problem there, what would be the problem in that case? Well, the problem is that Alice doesn't have a second last, because actually Alice is the last and the first, so there is no second last position in here. So I have a special consideration in here when my size is equals to 1. If my size is equals to 1, I need to handle that in a slightly different way. So how will I do that? Well, once I define my last, which is the one that I'm going to return, I can have a special consideration in there, and I can just go and say, if the size is equals to 1, I just want to return. Now there is something else. If the size is equals to 1, again, we already said we're not looking for a second last because there is none, but still my size has to decrease. And there is something else that we need to keep in mind in this particular instance. So if my list has only 1 element and he's the first and the last, and I'm removing it, well, now my first has also has to go to null. First is equals to null, and last is equals to null. So this is a special consideration that we need to define just when my size is 1. So let's try this again, and let's see if we're happy with this. There it is. So I'm very happy with this because after I've removed Alice, I don't have anyone else to remove. Now, let's do one more try. Let's remove the last from an array, from a list that is empty, and let's see what we get. So when it's empty, we're getting a nasty null pointer exception. And so that would be my second consideration. If I have an array that is empty, there is nothing I can do. So the best thing I can do in this situation would be if the size is equals to 0, meaning that it's empty, I should just return to return. And I'm not gonna try to do anything else. So let's give this a go. Perfect. I'm not getting any last pointer exception because when I'm removing last, I'm just getting a null in there. Brilliant. Now, just to finish this video, we have created a linked list that allows me to add elements at the top, elements at the back, remove elements from the top, remove elements from the back, and also find an element in a given position. So we've done quite a lot in here. The only thing that I should have also, because all collections in general have those methods, should be a method called size. A method that allows me to know how many elements I have in the list. So I'm going to say public int size, and that's just going to return size. And also we're going to do a public boolean that is going to call is empty, that it's just going to return whether the array is empty or not. So return size is equals to 0. So if size is equals to 0, it's going to return true. If size is not equal to 0, then it's going to return false. Now, one final reflection on this topic. Linked lists are amazing structures. They're very flexible and powerful. But something that we haven't mentioned is that they're particularly good for stacks and queues. And if you think about it, why? Well, it happens that stacks, in a stack, I only have access to the top element. My bottom element is not going to be there. And this is exactly what I have in here. I have a structure that I have access to one top element. And I also have, and in the case of the queue, I can add elements to the back and remove elements from the front. And that's exactly what I have in here. They look after the relative order, and I can implement a stack in a queue with this linked structure without having to worry about capacities or without having to worry about arrays. This is a very, very powerful tool. So what I would recommend you to try to do is try to create your own stack and your own queue, using a linked structure as opposed to an array list or as opposed to an array. This would be a really, really good exercise for you to understand how this structure works. Okay, all this code is going to be open Moodle. Thank you very much for watching, and I'll see you in the next one.